Hello everyone. Our group members are Disha, thakre, maheshwari, shahane and janvi, kaiskar. We are from Rashtrasanta Tuकडोजी Maharaj Nagpur University campus. Today we are going to discuss about the three-dimensional square well potential. So let us consider a square well having the dimension A. We are studying the square well by using the Schrödinger's three-dimension equation. In case of the square well, the potential inside the square well is constant and potential outside the square well is the zero. Now look at this diagram. This is the square well having the dimension A. We are talking about the potential. So this square well is the finite depth. So if we move along the negative direction, its potential become minus V0. Potential is denoted by V0 and we are moving in the negative direction. That's why it is minus V0. Now look at this equation. V of R is equals to minus V0 where R is between 0 to A. Means this potential is inside the square well where R is between 0 to A. And it is equals to 0 when R is greater than A. Means it is outside the square well where A is the radius of the sphere having the spherical symmetry. Now we are considering the Schrödinger's three-dimensional equation. The potential inside the square well R is between 0 to A. Then the equation becomes 1 by R square d by dr of R square dr1 by dr plus 2 nu by h square V0 minus mod of E minus L of L plus 1 divided by R square into R1 equals to 0. This is for the potential inside the square well where R is between 0 and A and L is the orbital angular momentum. Give this equation as the equation number 2. Now similar equation for the potential outside the square well, that is R is greater than A, then equation becomes 1 by R square d by dr of R square plus dr1 by dr plus minus 2 nu mod of E by h square minus L of L plus 1 divided by R square into R1 which is equals to 0. This is for the potential outside the square well.
Hello everyone, I am Disha thakre. I am going to proceed further. As Maheshwari had already talked about, that equation number 2 and 3 are the radial equation in three-dimensional, which is the Schrödinger wave equation, where small r is the radial spherical distance and small l is the orbital angular momentum. Now to solve it further, we consider the simplest case in which L is equals to 0, that is the particle is in the ground state, which is the S state. For this we consider that capital RL equals to U by R, K1 square is equals to 2 mu E upon H cross square, K2 square equals to 2 mu upon H cross square V0 minus E. After substituting equation number 4 in 2 and 3, we'll get new equations which are given by 5 and 6, and they are d2u by dr square plus k2 square u equals to 0 for r greater than 0 and less than a, d2u by dr square minus k1 square u equals to 0 for r greater than a. Now the solution of these two equations are been obtained by using the operator forms, which is, so we consider for equation 5, let d square plus k2 square operated on u, which is equals to 0. Now this operator equation can be written in an auxiliary form, which is m square plus k2 square equals to 0, that is m square equals to minus k2 square. So m equals to plus minus I k2. Now these are the roots of equation number 5. So using these roots, the solution of this equation for the root plus minus ik is given by equation number 7, which is u of r equals to a sin k2r plus b cos k2r. Similarly, if we want to solve for 6, we consider the same term, that d square minus k1 square operated on u equals to 0. Writing this equation in an auxiliary form, which is m square minus k1 square equals to 0, so m square equals to k1 square. So the roots are m equals to plus minus k1. So for this term, the solution is given by equation 8. So Using this general mathematical tool, we'll get equation number 7 and 8, which are given by UR equals to A sin K2R plus B cos K2R, UR equals to C exponential minus K1R plus D exponential K1R. Now the next step is to consider the boundary condition. As we have two boundary conditions, which is for R tends to 0 and R tends to infinity. For R tends to 0, equation number 7 can be transformed. So say if R tends to 0, then UR tends to 0. So after substituting this term, we'll get 0 equals to, as sine of 0 is 0, so 0 plus cos of 0 is 1, B. So B will become 0. So from this, we'll get a new equation, number 9, which is UR equals to A sin K2R, since B is equals to 0. Similarly, for the second case, we'll consider that R tends to infinity. So as R tends to infinity, the second term, which is D exponential of R, which is infinity, that will tends to infinity. So we'll neglect the second term, so we consider that D is equals to 0. So as soon as we consider this term, that D equals to 0, we'll get the second equation, and that is given by UR equals to C exponential minus K1R. So these two equations are obtained after substituting the boundary condition. Now the next step, we'll consider the continuity condition on UR and du by dr, which is at R equals to A. So for this, equation 9 and 10 are being equated. Thus, the first equation is A sin K2A equals to C exponential minus K1A, which is simply equating 9 and 10 by substituting R equals to A. Now in the next step, we'll differentiate both the equation 9 and 10 and equate it. So after differentiating equation number 9, the term will be A, sine will become cos, which is cos K2A, and the constant will be taken out, which is K2. Similarly for the 10th one, it is C exponential minus K1A and the constant term, which is minus K1. Now we'll divide equation 12 by 11. So as we know that cos by sine is cot theta, so as soon as we divide 12 by 11, AE will be cancelled out, so there will be K2, and cos by sine is cot K2A. That is actually, which is K2 cot K2A equals to the right hand side, the C and this term will be cancelled, we'll get minus of K1. So this is the required equation for the Schrodinger square well potential in 3 dimension. This is similar as it was been observed for the one-dimensional case, which is given by Ka cot Ka equals to minus alpha A. Now we can observe that there are different cases for n equals to 1, n equals to 2, and n equals to 3. Using this different case, we'll understand that how the particle will behave in the different quantum state, having energy level at n equals to 1, n equals to 2, and n equals to 3. The last equation, which is this one, which is pi square h cross square upon 8 mu, which is less than v naught a square, and v naught a square is less than equals to 9 pi square h cross square upon 8 mu. This indicates that the potential is bounded between 0 and A. That means the particle is bounded between 0 and A. So these equations are very much applicable to understand deuteron particle. As we had already considered initially that the orbital angular momentum is 0, that means the particle is in the ground state. So we are generally understanding about the smallest particle, which is the nucleus of an hydrogen atom, which is deuteron. So understanding the nuclear force will help us to understand nuclear physics. That is the application of this 3-dimensional square wave potential. Thank you.